Hello and welcome to my Material Science Final Project 2023. The topic I chose is wettability and what it means for some engineering applications. Throughout the video, you will see my references pop up on the screen, and let's start with an overview. We'll first talk about what it means to be hydrophobic versus hydrophilic, go into what a contact angle is. Section 1 will be material factors, common materials that are used, and themes found throughout the literature I read. How surface energy, grains, and polarities in a material affect the contact angle or wettability. And lastly, we'll go into environmental factors such as surface textures, impurities, cleaning methods, and how any of these variables can also affect the wettability, according to the papers that I've read. First, let's discuss what it means to be hydrophobic or hydrophilic. Take any flat surface. If you put a drop of water onto it, it will behave in a few manners. It might bead up really well, it might spread out a lot, or maybe it'll do something in the middle. In this video, we are going to refer to this as wettability, or you might have heard it also called a wetting property. But why does this even matter? In the study listed at the top of the screen, the experiment was to take carbon foams at different pH levels to see how well they absorbed oil. This could have possible applications in cleaning up oil spills in the ocean. But now let's talk about silicon wafers. Let's say you have a wafer here that has a whole bunch of semiconductor chips on it. You want to manufacture the most pristine, robust chip possible. And you might have guessed that wettability plays a role in this process. Something a little more familiar might be a leaf found in nature. And what happens when it rains? Water lands on the leaf and it rolls right off with no problem. This is called a hydrophobic property of the leaf. The opposite of this would be called hydrophilic. All of my references at some point reference hydrophobic and hydrophilic nature of surfaces. Let's go back to our wafer. There's a set of procedures within semiconductor manufacturing called photolithography. Part of these processes involve dispensing photoresist onto a wafer, which needs to spread out, meaning that the surface of the wafer is hydrophilic to photoresist. Consequently, if a drop of water is put on the wafer, it should act in the opposite way, meaning in a hydrophobic manner. The water will bead up instead of spread out. This is a trend that is commonly used to test the surface of a wafer. Let's quickly discuss contact angle. Here I'm drawing 4 different water droplets on different surfaces. I'm now illustrating the different contact angles. The droplet on the left has a high contact angle. The droplet on the right has a low contact angle. Therefore, the droplet on the left is on a surface that is hydrophobic to the liquid, and the droplet on the right is on a surface that is acting hydrophilic to the water. I chose 3 categories to discuss that each have effects to these surface conditions: material factors, surface energy, and environmental factors. Let's start with materials. Carbon is mainly used in these 4 studies, graphene in these 2, silicon in these, silicon carbide in this study, and metals and ceramics in this one. 2 studies in particular focus on carbon-containing materials. This study uses natural graphite, highly ordered pyrolytic graphite, graphene, and multigrain graphite. Another study uses epitaxial graphene grown on the surface of the wafer. This is because carbon-containing materials are naturally hydrophobic. Now that we know what surfaces are used, let's see how the surface energy affects them. When you have a freshly cut wafer, it is exposed to the air. This causes surface contamination and oxidation. A silicon dioxide film quickly forms on the surface, which will hinder its properties. Now let's look closely at the crystal structure. If you take one of these materials, I'm drawing 3 arbitrary planes through them. If you cut them along these planes in different directions, there will be a different number of bonds exposed to the air. This study calls them dangling bonds, which causes the material to have a higher surface energy depending on how it's cut. A higher surface energy can lead to a more absorbent surface and better wettability. To summarize the findings of these 3 studies, a surface that is exposed to the atmosphere will quickly become contaminated. High surface energy will make this process even more rapid. This can happen because of contaminants such as water, dust, or anything that the surface grabs out of the air. Going back to our vocab word, a conclusion of this study was that improved adhesion is caused by a higher polarity, which leads to a more hydrophilic surface and better adhesion. This was concluded in paragraph 7 of the results and discussion of this 2010 study. Just a reminder, when we say small contact angle, we're looking at this. How is contact angle affected by polarity? We know that when we have 2 polar molecules, they will be attracted to each other. As we know, water is a polar molecule. Therefore, if our surface is also polar, it will want to adhere to the water. This study found that as adhesion increased, the polarity had also increased. Now we've seen some different things that either cause or disrupt a material from adhering well to a wafer, or any surface for that matter. So with all this, what can we do to promote adhesion? Because ultimately, we want photoresist to adhere well. First of all, there are chemicals called adhesion promoters. Apart from that, you can also make sure that the surface is clean, that there is an optimal roughness, and that the substrate you have is pure. Sometimes contamination can't be avoided because of certain processes in the manufacturing of a wafer. However, there are ways to clean a wafer. These 6 studies reference methods such as annealing, plasma treatment, as well as some less intense methods such as using alcohol and DI water. To reiterate, why do we need all these things to promote adhesion? Why can't the photoresist just stick to the wafer? Again, this is because of things like silicon dioxide that oxidizes on the wafer, or contaminants that are in the air such as dust and water. Last but not least, we have environmental factors. I want to start off by saying that there's no such thing as a perfectly smooth surface. Given our arbitrary surface here again, if you zoom in enough on one tiny part, you will see that the surface actually does have some texture. This is because of a characteristic called roughness. It needs to be considered in wetting experiments. All surfaces have a roughness, but some surfaces have better wetting properties than others. Based on what we know so far, would you guess that a rougher surface would be more hydrophobic or more hydrophilic? The answer might be a little surprising. In the first study listed here, it was found that a hydrophobic surface would become more hydrophobic with more roughness, or as they word it, microstructured. In the second study listed here, it was found that a rougher surface would have a stronger hydrophilic property. Well, how can it be both? It turns out it actually is both. In the third paper listed on the screen, it is stated that a hydrophilic surface would become more hydrophilic, and a hydrophobic surface would become more hydrophobic if it is rough. This is quoted from this third article, section 3.3, paragraph 1. What does this mean? If a surface is already hydrophobic, it will become more so, and if it is hydrophilic, it will also become more hydrophilic. This was a video on the properties of surfaces that affect wettability as well as contact angle. Thank you for watching.